welcome to another AQA AS chemistry video. Today I'm going to be doing a video basically answering questions that will come up. I'm not going to be doing an explanatory video today. I'm going to be just doing some questions based on the content that we've covered so far. So it's going to be about the mass spectrometry and working out the relative atomic masses based off abundances, that type of questions. I've stole this question from Seneca, and I also have some past paper questions that we're going to go through today from the actual exam, from previous exam years. So yeah, let's get straight into it. So got a question here. So a metal atom has two isotopes, M72 and M75, in their respective percentage abundances. Should be that percentage abundances there. The AR of this metal M, we don't know what it, we don't know what the name of it is, but it doesn't really matter to us. It's not really relevant to us. We know the AR of this metal M is 73.2. Now the question is to work out the abundances of each isotope, assuming of course that these are the only two isotopes of this element. Right, so this isn't what we usually how we usually do it, because usually what we're trying to work out is we're trying to work out what the MR is using the percentage the percentage abundances and the isotope mass numbers. However, we're given the mass numbers and the percent and the AR, and we're told to work out the respective abundances. So we have to just rearrange it a little bit and try and work out, because this could happen in an exam. You could get this question, it's going to ask you to work out the AR. Right, so you just need to understand what's actually going on. So what's actually going on here is that you get the AR. The AR is equal to the sum of the isotope abundances, isotope mass number, isotope mass number multiplied by the isotope abundance. And then that's all over the sum of isotope abundance. And the sum of isotope abundance in this case would be 100%, if 100, which is just because we're doing it by percentage, right? So it's all going to be over 100. So if I was to write this out, so 73.2, if I was to write this out, what we actually have right now, that's equal to the sum of, in this case, because we only have, they said these are the only two isotopes, so we actually have to write this part out. These are the only two isotopes of this element. It will be 72. Let's call it X. Let's call our first abundance X. Now it's not an easy thing that we're doing here, because we have both X, and I'm going to show you here because we have 72X and 75Y. We have two factors, both X and Y. This question requires a bit of, and it's going to be all over 100, like I said before. This question is going to be a bit more, not an easy substitution, because we have both X and Y. How are we going to solve for both? I'm going to show you how to do that. So we know, because this is a percentage, we know these are the only two isotopes of this element. So we know that X and Y together must equal 100. X plus Y equals 100. And let's say that we wanted to just isolate, we just want to work out 1. How would you do that? If X plus Y equals to 100, let's say you just wanted X, right? X would be equal to 100 minus Y. Or if I want to just do Y, for example, let's just do Y, okay? If we want to just get Y, we can separate. So X is equal to 100 minus Y, and we're gonna have, let's just say the idea of working this out is to only have one factor in here. You don't want to have both X and Y. It makes it too confusing. Let's just go for Y, right? So that means that 73.2 is equal to, if X is equal to 100 minus Y, then we can do 72 times, right? Actually, that's a terrible 7. 72 100 minus Y plus 75Y. And that's all over 100. We multiply it over to this side, so let's simplify what we have now. That's 7,320 if we was to multiply, if we could get rid of this denominator of 100, multiply it to the other side. So 7,320, if we multiply that by 100, is equal to 7,200, because we're timesing 72 by 100, just expanding the bracket, minus 72y plus 75y. Bring this over to this side, 120. Oh, 100, yeah, 100. I'm sorry, this is not working with me right now. 120 is equal to 3y, which means that y. Why is this not working with me today? 40. Y is just equal to 40. Now that we know that y is equal to 40, we can now work out what x is, because remember we know that x plus y equals to 100. That means that x, as you have here, x is equal to 100 minus y. So that means that x would be equal to, and we know that y is equal to 40, 100 minus 40. Therefore, x is equal to 60. And therefore, we know that the relative abundances of M72, the abundance of M72, now I can write a little thing here. The abundance of M72 and M75 are 60% for, so x was 70, yeah, so 60% or 0.6, but they want it in percentage, so 60%, and y is 40%. And that's how we would answer this question here. There's also now another type of question that you get in your exam. So that's done now. I'm going to move on. That's the first type of question that you get. Now let's go on to a mass spectrometry question. Let's go. I have quite a few of questions that we're going to go through here. So, yeah. If I ever found a pen, great. So, this question, I'm telling you now, know how to answer this question. It always comes up every year from what I've seen, and it's always an easy 5 or 6 marks, and it's always the exact same concept as I said before. So it's a mass spectrometry question. So let's read it out. Let's read it out. So the question is, a chromium 53 plus ion travels along a flight tube of length 1.25 meters. So it's a mass spectrometry question where we have the tube, and the tube is, they tell us now the tube is, this isn't terrible, this is just a diagram, but you get what I'm trying to say here. The tube is 1.25 meters long, right? The ion has a constant kinetic energy of 1.102 times 10 to the power minus 13 joules. Remember what we said before, that the kinetic energy of all particles is the same, and the speed is dependent on the mass of the compound. So all particles, we know for a fact that all particles will have this kinetic energy. So they've given us the equation, and they said that in this equation, the mass is represented in kilograms, which is important because this is where people drop marks, and the speed is in meters per second. And the question is, calculate the time in seconds for the chromium 53 plus ion to travel down the flight tube to reach till it reaches the detector. So how long does it take to get from here to here? And they've given us the Avogadro constant, which is this here, 6.02, which is always a constant, 6.022 times 10 to the power minus, times 10 to the power 23, which is the amount of particles in 1 mole. Is always going to be that many in 1 mole. Right, so if I was answering this question, what I always do, I'm not doing this in time conditions because I'm trying to explain to you as I go along, but you should be able to do this within 5 minutes. Always do a mark per minute in chemistry. I know you get a bit more time, but always do a mark per minute in chemistry. The first thing I'm always doing when I do this is, sorry if I'm waffling a lot, but I'm just trying to explain every little part of it so you can understand. I write out this equation, V is equal to S over T. And then I'd say we're trying to work at the time, right? So T is equal to S over V. And it's like, okay, so we actually have we want to work at the time. We actually have the distance already, so we don't have to worry about the distance, but we don't have v. But it's given us the equation here, right? But we need to rearrange this equation in order to get v by itself. So if I want to get v by itself, it'll be 2ke. Don't worry about showing the examiner each stage of rearranging the equation. Yeah, you actually only get a mark for just for rearranging the equation. Like you have to do 2ke is equal to mv squared, and then just make sure you do your answer correctly, but you do get a mark for rearranging your equation when it comes to this type of question, but not for every question. But for this type of question, you do usually get a mark for actually showing you've rearranged your equation correctly. So v would be equal to 2ke over m, and then the square root. So it's the square root of, if you didn't get that, I can do a bit slowly for you, but as you see here, 2ke, because I move that over there, and that's equal to mv squared. And if I want to have v squared is equal to 2ke over m, and then v by itself, square root that. Right, there. So now we have that. We have the energy, we have the amount in joules, but we don't know where it is in mass. We need to work out the mass. How are we going to work out the mass? We know that mass is equal to moles is equal to mass over the mR. But we still need to work out what the mass is. Now, if we know that, we need to work out the mass. mR, we know, is equal to the mass over the moles. We have the mR. The mR is 53 for this compound. But we need to work out the moles. So we need to work out the mass, by itself. We don't need this and this. So how are we going to do that? They've given us the Avogadro's constant here. Now, this Avogadro's constant is 1 over the moles. So if I did, what would actually do, what I would do, is I would divide it, and I'll explain why. Because if we know that mR represents mass over moles, and L, which is what Avogadro constant is being represented, is 1 over the moles, m over n over that would actually cancel out that and that. But to show you exactly, in case you didn't get it, do this. And that's the same as divides by 1 over moles, right? Because moles to the power of -1. So that over that, same thing, right? That's the same as if you're doing this, keep flip change, simple maths. That cancels out, that cancels out. You're now left with m over 1, which is just the same as m, the mass. So we know now that we have the mass, so I would do, so working out the mass, we need to know that we do the mR, as I said before, we just proved now if you do the mR over Avogadro's constant, we get the mass. So 53 over 6.022 times 10 to the power 23 would equal I'll say it again, make sure I'm doing this slowly for you guys, because usually you should be nearly finishing this question by now, but I'm just doing it slowly so you can understand what I'm trying to do here. If you need to speed up, if you feel like I'm going too slow, you can go ahead and skip to where my answer is, and hopefully that makes it better for you if I'm going a bit too slow for you, but I'm just trying to explain it for you guys. Anyway, so it's 8 point, the actual answer is 8.801 so and so on times 10 to the power -23. I'll be looking at which question in reality I represent it. I'm just using this, I'll just be using this value, but I'll look at the question. What's the lowest number of significant figures in our question? Here's 3, 4 here, 4. This one here is low, so 3. So I'd use 8.80 times 10 to the power of -23, and that's actually grams. Usually that's actually grams. When you're using Avogadro's constant, when you're using the mR is usually done in grams. But remember, this needs to be, as I said, it's important to remember that this this is where a lot of people drop marks. It's only you only usually drop a mark because it's a conversion, but you want to make sure you maximize your marks, and people forget it's kilograms and leave it as grams. So you have to convert this, and you get a mark for this saying to convert this to grams, so that the mass, I should have wrote it here. The mass of Cr chromium 53 plus is equal to that is 8.80 times 10 to the power of minus 23 grams here, but we need it in kilograms. Going to split this in 8.80 times 10 to the power of minus 3. You get a mark for this, by the way. I'll probably go through where the marks are before. Times by 10 to the power of minus 3. In order to go from grams to kilograms, you're dividing it by 1,000, or you can just times it by 10 to the power of minus 3. And that's 8.80 times 10 to the power of minus 26 kilograms equals the mass of 53 Cr plus. We're not done yet. Now that we have that, we can finally substitute that value into here. So the V is equal to the square root of 2 times by 1.10, or this value here, 1.102 times 10 to the power of minus 13 joules over the mass that we now have is 8.80 times 10 to the power of minus 26. We now put this into our calculator. Right, so square root 2 times by 1.102 times 10 to the power of minus 13 over answer. You get this number here, right? You get this massive number. And if you get this massive number, you think to yourself, oh, I've done something wrong, or I've messed up, because that's a really massive number for, that's your speed. Your speed is 1,582,480. Don't freak out. That's right. That's the correct answer. You have to understand that these atoms are moving extremely fast. You know, they're going from here to here in a very, very fast manner. So if you get an answer like that, don't think to yourself, oh, I've done something wrong. That's correct. That is correct. Because this is in meters per second, right? So don't freak out if you get a massive answer like that. It's correct. How to represent it? 3 significant figures, really, but I actually just write it out as I mean, I'd never seen them, take marks away from you from writing out this as it is. It's only the last answer, which is where they really care about you dropping your marks. You don't have to rewrite the 0.022, but I'd write it out, but don't actually have to write that part out. So I'm going to put it in. Now we've got the V. We're not done yet. We're nearly done now. The T, the time, which is what we care about, the distance, 1.25 meters over our velocity, which is now, we know is that 15820. Yes. And our time is, so 1.25, right, over answer 7.89. Well, we round that up because when we're doing 3 significant figures, 7.90 times 10 to the power of minus 7. 7.90 times 10 to the power of minus 7. Now, I think this is the correct answer. I haven't checked the correct answer, so I could be very wrong, very, very wrong. But this is how I would do it, and this is from my experience what I would do, and that's seconds. 7.90 times 10 to the power of minus 7 seconds. Let me try and find the correct answer. I remember putting it here. If I'm wrong, I've just messed up the entire video, but hopefully that is the correct answer. Alright, so then 2.5. Yes. Yes, okay, good. Yeah, that is the correct answer. Where you get the marks are, they say the marks are for, oh, I should use a different colored pen, but I don't care right now. I'm just going to use this to show you. You get a mark. M1 is for doing, is for this, showing this. That's M1. M2 is for the rearrangement of this. So this gets your mark. So either that in itself can get you the mark, or writing out this. So if you do any of these two, that's the second mark. So I should say M1, M2. Don't teachers use this space to actually write? I can just write on here now. I don't care about that. A mark for this, distance over time. You can write S over T or D over T. I mean, it represents the same thing. I doubt they'd really drop a mark for you for writing S instead of D, but I mean, write D instead. It's not. I mean, it's not displacement, so it should be D actually. I always write D in the exam, S in the exam, but it is D. My bad. It is distance, not displacement, so that is wrong. But that's what you get, and then rearranging it into. Actually, no. No, you don't even need to rearrange it. You can just get a mark just for saying that. That's M4. M5 is to actually getting the final exam. So getting the final answer, which is times 10 to the power of -7, should be a bit more. That's where you get your mark. That's M5, or just M5. All right. And then now, so I'm gonna go into a different question here. I'm gonna let you guys do it. Now I'm gonna let you guys do. So I've got this question here. I want you to go ahead and answer this question here. And then when you're done with this, if you get done with this, pause the video now if you want to go and do this. So do this, and after that, this same concept, just go through this question again. So this it's a similar type of question as before, but I want you to go and try and do this one by yourself. And yeah, so good luck trying to answer this question. I'll give you pause the video now, answer the question, and then we'll go ahead. All right, I'm gonna assume that you've paused the video now and you've done the question. You should have enough time to do it. So the question is, the time of flight of mass spectrometer can be used to analyze large molecules such as the pentapeptide leucine encephaline. As I said before, they can use this to work out polymers such as proteins or DNA samples. P is analyzed, so they're saying you can just represent this by P, right? And P is ionized by electrospray ionization, and its mass spectrum is shown in figure 2. Great, so describe the process of electrospray ionization, given an equation to represent the ionization of P in this process. So remember what electrospray ionization is when you dissolve your compound into a solvent. You push that compound through a nozzle or a very thin tube, and then you apply a high voltage. So say P. What I would do is dissolve compound P in a solvent. I'll still do this as more. I just bullet point. You can bullet point, unless it specifically says they care about the quality of written communication. You can just bullet point these questions. So dissolve compound P in a solvent. I'd say this is describe. It doesn't say explain. So I was about to explain. I was about to make the mistake of explaining and saying how it does it, where the proton gets ripped off the solvent and then it gets added to the compound. But you don't have to say it. Just say dissolve your compound P in a solvent. Inject. I say pass through pass dissolved compound via a nozzle, or we can say a fine tube, I think you can get away with maybe, and then apply a high voltage. They would also say apply a high voltage. Guys, I think personally, writing answers as bullet points is better because you can just see, I say that's one mark, that's another mark, that's another mark, and you're allowed to bullet point in the real exam. That's how I did it as well. Bullet point your answers. You know you for sure I've got the mark here. Well, at least I know I've said the mark here, said the mark here, and said the mark here. Other examples like in biology in the essay, I have to write. Obviously, you can't bullet point, but in these, there's nothing stopping you from bullet pointing, and they'll mark it the same way, and it makes it easier for the person marking your exam to see where you know your points, right? And so, and they said given equation to represent the ionization of P. So this ionization is gaining a proton. So I would say P plus a proton, which can be represented by H plus, goes to form P H plus. That's how I would do it. And I'll go and find the answer later on. But on to the next part here. I assume you've done this part. I gave you enough time to go and do it. If you still haven't done it, pause the video now and do the question. If not, if you have done it, done it. What's the relative molecular mass of P? Careful with this one. So we know that this one here is 556. Don't be tempted to go 556. Remember what we've done before. This MR is not the same because we've gained a proton. With electrospray ionization, we're gaining a proton. So technically, it's not. It's one more than what it actually is. So it's 556 minus 1 because remember we gained protons. So the original compound had 555 protons in it. Sorry, not protons. Sorry, 555 as its mass, as its molecular mass, as its relative molecular mass, or as MR. The MR is not 556, it's 555. You have to take away one proton, so that's why I would say 555. All right, now, a molecule Q is ionized by electron impact. So not electron ionization. This is now another compound. They're doing electron impact ionization in a time of mass spectrometer. The Q plus ion has a kinetic energy of 2.09 times 10 to the power minus 15 joules. This ion takes 1.23 times 10 to the power minus 5 seconds to reach the detector. The length of the flight tube is 1.5 meters. Calculate the relative molecular mass of Q. And they're giving you Ke is equal to half mv squared, where m is the mass in kilograms and v is meters per second, and the Avogadro constant is so. Right. Let's always write what we have. So v is equal to d over t. They want us to work out. So Ke they've already given us here. Let's try and work backwards to what we're trying to achieve here. If we want to work out the MR, I've always said, what did I say before? It was to work out the mass, it was the MR over L. The MR is equal to moles equal to mass over the MR. MR is equal to the mass over the moles. Okay. Sorry, sometimes I might make that mistake. I always write out my equations just in case I forget. Make sure I don't make a silly mistake. So we have, right, we're trying to work out the MR. We need the mass and we need the moles. Alright, so how I'd go about this is then I'd rearrange, we need the mass first of all. In order to work out the mass, I can work out, I have this equation, I have mass here. Right, so we need, so 2K, if I want to work out M is equal to 2KE, or yeah, divide that by half. So yeah, so 2KE over V squared. And we have, I'm pretty sure we have V squared. Do you have V squared? No, we haven't got V squared, but we have got V. We've got V, right? So V would be equal to the distance, which is 1.5, over the time, which is the 1.23 times 10 to the power minus 5. V would be equal to 1.5 over that, so 1.5 over 1.23 times 10 to the power of minus 5. 121,951, so and that's in meters per second. Actually, no, that's it, meters per second. Great. We have that now, so we have v squared. Now we can work out what m is, so m would be just be 2 times by 2.09 times 10 to the power minus 15 over 121,951 times 10 to the power of, no, sorry, not times, just squared. That m would now be equal to 2 times by 2.09 times 10 to the power of minus 15 over our answer squared. You should get something along the lines of 2.81. The mass is 2.81 times 10 to the power of minus 25. And that should be in kilograms. That is in kilograms because all our other values are in kilograms or kilograms. If I wanted to get this in grams though, because we need to work out this in, yes, I do this in grams because we want to work out the MR. So I do 2.81 times 10 to the power of minus 25 times by 10 to the power 3. And that's 2.81 times 10 to the power of minus 22. That's grams, and that's the mass of Q. Equals the mass of Q, or I guess Q plus really. And what have I said before? If I want to get the M, what was the work? I calculate the relative atomic mass. I would multiply it by L. How do I work out this now? So if I want to have to get from, if I want to work out the MR, I have M over N. And I want to, actually no, I want to take away N. Right, that's great. If I want to take away N, I'll just times it by 1 over the moles, which is just L. So MR would be equal to mass. So I have this. Sorry, I have the. If I want to work out the MR, I have the mass. I have the mass times by the Avogadro's constant. So mass times by 1 over n, and that's the same as m times. That's the same as m over n. So MR would be equal to mass times by L. So MR is equal to 2.81 times 10 to the power of minus 22 multiplied by 6.022 times 10 to the power of 23. You should try and write this in one small line, but I just don't care for the sake of it. Do this in one straight line. Don't follow me. Actually, at this point, I'm not really doing this for time-wise, so I guess I would just do it. Let me just show you how you should do it. 2.81 times 10 to the power of minus 22 multiplied by 6.022 times 10 to the power of 23. The MR would be equal to, so I times that by, that's 6.022 times 10 to the power of 23. You should get an MR of 169 0.25. I mean, they want it in three significant figures. All the questions are in three significant figures, so I'd leave it as just 169 to be honest, but I guess you could show it was 169.3 if you rounded it, but I'd leave the MR as 169. Great. Hopefully this was, I'm doing a part 2 for this video, so yeah, bear with me.